The presence of rotating damping gives thus to skew symmetric terms in the stiffness matrix, that is, to a circulatory matrix. This is the total stiffness matrix with the first term, that is the typical elastic stiffness, plus omega that multiplies a skew symmetric stiffness matrix, skew symmetric, anti-symmetrical, that is the circulatory matrix. This is caused to rotating damping. Rotating. The circulatory matrix vanishes when omega tends to 0, as it should be expected. When this speed go to 0, the circularity matrix go to 0, vanishes. Spin speed, omega, spin speed. Vanishes. The rotor becomes a stationary system. From rotating to stationary. And its equation of motion becomes that of a natural system. Natural frequencies, natural system. Instead of writing explicitly the forces due to non-rotating and rotating damping, the equation of motion could be obtained by introducing the Rayleigh dissipation function. Into the Lagrange equation. Its expression is F equal to 1/2 of the non-rotating part proportional to Cn x point C plus y point C plus the rotational part in the rotational reference frame whose coordinates are C point C plus eta point C. reminding that C point C and eta point C are the R matrix, rotational matrix for X point C, Y point C, plus R point or XC, YC. Substituting, we have X point C squared, Y point spin squared, C squared, eta C squared are all elevated by 2. So X point C plus eta point C is this vector transposed for the same vector. In fact, the modulus of a general vector, the modulus squared, is the inner product of V per V. In the same way, we have F equal to 1/2 Cn X point C squared plus Y C point squared plus 1/2 of CR rotating parts per continue next page. 1/2 CR per the vector transposed, so X point C, Y point C transposed per R matrix transposed. Note that in doing the transposition, we have changed the sense, the order of the vectors. First, we have R matrix per X point C, Y point C. Now we have the inverse ordered vector transposed plus XC, YC transposed per R point transposed. This for the same vector not transposed. So R XC, X point C, Y point C plus R point XC, YC. This is an inner product. By performing the products and remembering that R transposed per R matrix for the orthogonality of the R matrix is the identity matrix, and that R point transposed per R point matrix is omega squared times the identity matrix. It follows that the Rayleigh function becomes 1/2 of the sum of Cn plus Cr x point C plus y point C plus 1/2 per Cr rotational coefficient spin speed squared plus xc squared plus yc squared plus the third term plus Cr omega x point C y point C transposed per R transposed R point xc yc. That is, the first part remain the same. Also the second, but simplifying the third term, we have plus Cr omega x point cyc minus y point c xc. So it's the product, the inverse programs of the two coordinates. Once was point and the other and next without point. By introducing this Rayleigh function into the Lagrange function, we rapidly obtain the equation d in the t that derivates in terms of time of the t minus u in the q point I minus the t minus u in the qi plus, this is the further term, the f in the q point I equal to qi. Also in this case, we obtain the matrix form that we have seen. M 0 0 M symmetric mass form mass matrix x2 point C y2 point C plus a symmetric matrix with the non-rotating plus rotating coefficient on the diagonal for x point C, y point C, plus the stiffness matrix, the stiffness symmetric diagonal matrix plus the spin speed multiplied a skew symmetric CR minus CR plus and minus skew symmetric. This is the circularity matrix that corrects the simple stiffness, and all this matrix multiplies XC and YC. All this is equal to the second part that contains the force terms due to imbalance and due to external forces. So, also in this case, it is possible to resort to complex coordinates. By multiplying in the same way the second equation and then adding, we simply obtain m per r to point C plus Cn plus Cr r point C plus k minus the imaginary part ICR omega per RC equal to, in a unique way, m epsilon omega squared exponential of I omega t plus Fn, non-rotating force. This equation is formally identical to the equation of motion of a mass m, suspended on a spring with complex stiffness. And a viscous damper with damping coefficient, that is the sum of non-rotating and rotating parts. So damping coefficient, that is total. On which a force with harmonic time history, with frequency omega, the speed, and amplitude m epsilon omega squared is applied, and a constant force is acting, constant. One, harmonic time history, the other constant time history. We have to remark that what is skew symmetric? Skew symmetric. In the we'll do a scheme in which we compare real coordinates with complex coordinates. So what is skew symmetric? Skew symmetric in real coordinates is imaginary when complex coordinates are used. This is a general rule. So, in real coordinates, we had omega per 0 plus CR minus CR 0 circulatory matrix, skew symmetric matrix. Now we have minus E CR omega, that is imaginary. This is a very, very general rule. What is skew symmetric in real coordinates is imaginary when complex coordinates are used.